So, all right. Okay. So, last time we ended up talking about how dendrites and their passive properties affect summation of input in neurons which have elaborate dendrites. And I ended up the class by explaining to you things that you probably have already heard from Idan, that there is a huge attenuation of voltage from the dendrites to the soma. And when we say attenuation, it means that the EPSP, or the voltage that develops in the dendrites, is getting greatly reduced by the time it arrives to the soma. And we tend to think that the soma is an important part for summation of input in order to reach the threshold. So if the synapse is located on the dendrite, and instead of producing some voltage in the dendrite, it produces so little in the soma, it means that most of these synapses on the dendrite do not contribute almost anything into the generation of the action potential.
When Idan showed it, he showed us the same information sort of, and he said that when it reached the soma, it's almost 50% than the information that you get when you stimulate the soma. Can you hear it?
It's much less, right? So it is true, and there is a mixture of two things. So what is true is that the voltage that arrives to the soma can be as low as 10% of the original voltage in the dendrite. But if you look at so I told you that one of the things that happens is that the peak is becoming smaller, but it's also becoming wider. So if you integrate under the curve, which is corresponding to how much current is reaching the soma, then this could be around 50%. Now, why does that happen? Because when you inject current to the dendrite, it charges the membrane in that location. So the capacitor, if you want, the capacitor-like properties of the membrane are charged, and this happens all along the way. So a lot of the current that flows, some of it flows directly, and some of it charges the membrane. But afterwards, it discharges. So a lot of the current you get back. So it's like the membrane is holding the current for a while, and then it's releasing it back. So you get a lot of current, but it doesn't produce so much voltage. Okay, and then this is something that is kind of complicated in the sense that it's not obvious what is important to make the spike. Okay, so all of you know that in the biological way that we think about it, we think that we have a voltage threshold, and if we reach the threshold, we get an action potential. Okay, but if you look at Hodgkin-Huxley equations, for example, these are equations of current. So what drives the spiking is current. So and in some ways, what drives the spiking is also the derivative of the voltage, because that's also important. You can get to the same threshold with less voltage or with less current if you do it fast enough. Okay, so the relation between what drives the spike and the spiking is complicated. So the voltage is important. So if you inject a lot of current but you'll never generate enough voltage, you will not spike. Okay, so the voltage is important, but the current is also important, and the derivative of the voltage is also important. So they are all it's a complicated system. Okay, that's why we look at all kinds of parameters. So one way to look at it is to see what would happen. So this is like a colorful color scheme of a Purkinje cell, and here you see what happens if you put an input into the soma. So red is like high voltage, and blue is low voltage, and you see that you have a attenuation of the voltage from the soma into the dendrite, but it's not huge, so you have to go pretty far away in order for the voltage to reach very low values. However, if you put a synaptic input of the same size in the dendrite, the decay is much bigger. So already kind of very, very close to the input, you're already getting into the green and very fast into blues.
Model or experiment? Can you measure it?
Okay, so this is a good question. So for a long time, you could only model it, and this is kind of one of the best examples after Hodgkin and Oxley, where theory basically preceded experiment. And we'll see even a few more examples of that. The issue here is it's kind of a biophysics more than theory. So it's like it's real physics in a way, but not like for physicists it's not very interesting because it's just like, you know, some pretty simple equations of capacitance and resistors. But for interpretation of experimental results, so the condition that happened was that people could record from the soma very easily, but they didn't know what happens in the dendrites at all, and there were a lot of arguments. I don't know if you heard about it. Idan likes to talk about that. So the person who developed this theory was Wilfried Roll, and the first paper that we'll present in the paper session is a paper by Wilfried Roll, and he started doing that at 57, okay? And he was working in a lab in Australia of John Eccles, who was later received the Nobel Prize for understanding synaptic integration. Eccles was the first person to record intracellular four mammalian cells in vivo. So they were recording from motor neurons of the cat in the spinal cord. Intracellular recordings already in 53, very, very early on. Very difficult experiments. And they did not know how to interpret the results. They kind of assumed that the synaptic conductance of proximal and distal synapses are different, all kinds of things like that. There are fast synapses, slow synapses. And Roll came and actually explained everything just by the passive properties of the dendrite. There was a lot of argument. Eccles didn't want to accept that. He didn't let him publish anywhere, and this first very influential paper eventually was published in a very anonymous journal. But it made a lot of impact because people realized eventually that he was right. Okay, so these are models. But today we can do the experiments, and the experiments that have been done proves that this is right. Okay. Now there is another implication, and this implication comes from the following thing. You see that if I inject a current in the dendrite, I get a lot of voltage locally. What does that mean? Why that can be important? So I give you here like first I'll show you the result, and then you'll try to explain to me why it happened. Okay, so we take a dendrite, a neuron with a dendrite, and it has like two of these thin distal dendrites. And we compare two conditions. One, when we activate two synapses, the blue and the red together. So each one of them is doing an EPSP. And when we activate the blue and the red, we get this magenta, which is like the mixture of the blue and the red. Okay. However, when we activate the blue and the green, which are the same, but it's as if we take this synapse and just move it over here. Okay. Then we get this blue line, or cyan line, which is smaller. Okay? This is what we measure in the soma. So if we put the two synapses together on the same dendrite, we lose voltage in the soma, rather if we distribute them in distal locations. What can cause that?
Channels are open, and then it causes a bigger leak of the current. Because like they increase the leak for each other.
Right. Okay, another way to look at it. It is kind of shunting, it's true, but I'm not sure if everybody knows what shunting is. Okay, not everybody knows what shunting is. Okay, so just I don't want to get into that too much, but I just want to give you the intuition, and the easier intuition to look at it, although it's not precise, is that the synapse is generating voltage locally, and this voltage is very high. This is because the dendrite is very small, the diameter is very thin, so you get high local voltage, also in this case. Okay. Now, if you remember, the current that flows through the synapse depends on the driving force, basically on the difference of voltage between the outside and the inside. So if I depolarize a membrane, I lower this driving force. Okay, there's less force that forces the current going in. Okay, if I would open, okay, so let me put it in a different way. Do you know, who knows what's the reversal potential of a synapse? Okay, you know that if I take an AMPA synapse, okay, and I hold the voltage at 0 millivolt, if I open the channels, nothing will flow in or out, because I'm at the reversal potential of the synapse. Okay, there is no driving force, nothing drives the ions in any direction, because we have like this mixture. The AMPA receptor is, it can allow also ions to flow in, but also ions out. So at 0 millivolt, we are exactly at the right mixture. So when one synapse is opening, it kind of reduces the driving force for the other one, and then together they produce less voltage. Why is it less voltage? Because we saw that we have huge attenuation between the two. So the blue synapse is reducing the driving force for the green synapse by this much, but for the red synapses only by that much. Okay, because when we take these synapses apart, they stop influencing each other because the voltage that flows between them is attenuating, like here. Okay. If you don't follow, we can come in the break. I can explain to you in more detail. So this was more or less the picture for many years with theory, with not so much of experimental support, except we had some support for this phenomena already from motor neurons in the spinal cord.
For the graph in the middle, so it's change state or steady state.
I think this is steady state. I don't remember actually. I think it's steady state. Okay. However, already in 1979, there were early examples for the fact that dendrites are not completely passive. So they also hold some ion channels. So the first people to show that, this is a paper by Linas and Sugimori, and they basically took advantage of the fact that Purkinje cells are organized very, very nicely in the cerebellum. So if you slice the cerebellum in some way, actually I think this was even in vivo, if you put your electrode and you measure the distance that you go in, you know when you arrive to the area of the soma, just by the distance. Okay, so if you hit something before and you record, and it's like higher, then it means that you are not in the soma, and there are no other cells there. There are few inhibitory neurons, but they are very small and very easy to recognize. So if it's not inhibitory neuron and not Purkinje cell, there's nothing else. It could only be dendrite. And then they found out that when you record from the dendrite, you might actually get some kind of action potentials in the dendrite, and you can also you see that you have like every time the cell is spiking, you get these huge thing in the dendrites, okay? But you have these relatively small things as well, and this corresponds to these spikes in the soma. So you see, you have like these big, you have these big spikes in the soma, and when they arrive to the dendrite, they are very, very small. Okay, but sometimes you get these huge events, and I don't know if you heard, but Purkinje cells have two types of spikes. They have what is called the simple spike. These are very fast spikes, but they have also these complex spikes that usually looks like that. So you see, you have like this spike and then some other spikelet. It's a very long thing. It happens almost. It takes almost 10 milliseconds to end. So these things you can see in the dendrites. Okay, the big things, the complex spikes you can see in the dendrites. So this was the first evidence that while the regular spikes do not go back to the dendrite, the big ones do. And this kind of an evidence, and you can also use pharmacology to block some currents and see that there's a lot of involvement of calcium in this phenomena. So this was the first evidence that dendrites are not as passive as we think. I just want to, before I show you the more convincing evidence in a way, in many details, I just want to show you also that there was a long-standing question for pyramidal cells. So if you do a model of a pyramidal cell and you measure what will be the difference in amplitude in between synapses that are located on the dendrites and on the soma. So what we do here is we take a synapse and we place it on the soma, measure the voltage, then move it along different dendrites, and at each location we kind of activate the synapse and measure what will be the voltage at the soma. Okay, and we repeat it like 1,000 times, and every time we measure, and we put the color of the voltage in the soma at the location of the dendrite. So when this is blue, this means that the synapse here almost does not produce any voltage in the soma. So what you see here is that so if the synapse is located on the soma, it will make something like 0.5 millivolt. 0.5 millivolt means that if you need, say, 15 millivolts to reach threshold, okay, so you need something like 30 synapses together to reach threshold, okay? If all the 30 synapses will arrive together at the soma, we will get to threshold, which is about 15 millivolts above the resting membrane potential. But if you get to here, you can activate all the synapses because each one of them is producing, tenths of that. Okay, so you need hundreds of synapses together in order to generate this spike. Okay, so basically the synapses that arrive more or less from here onwards, they kind of out of the game. They don't do anything. And this is also true for for the basal dendrites that are usually just many of them are cut, but they're also not contributing very much when you go to the distal part of them. So this opened the question of like that doesn't make much sense. Yes.
Sorry. So you mean the dendrite that close to the soma have more contributed than dendrite that far away?
Right.
That's contradictory with what you don't say.
In what sense?
Yeah.
Yeah, right.
And he said that every dendrite is important.
Yeah.
Don't neglect anything.
Okay, I mean, first of all, we are not done yet. We haven't finished yet. Okay? No, we cannot neglect anything. But let's come back, one step backwards to this theory of thin-fire chains of Abeles, where you need some inputs coming together in order to drive fast the input into the threshold and make a spike. Okay? If we'll take all these synapses, say we have hundreds of them, and we'll place them here and very far away on the dendrite. First of all, they're slow, so even if they're arriving together, they have this very sluggish way until they get, to the peak. And also, each one of them is contributing so little that it's actually almost impossible to implement this model with real neurons. That's what I'm saying. When we assume that the dendrites are passive. Okay? So this is
They're not.
wait.
I mean,
We're going.
standpoint.
Okay, so we're going slowly. We're starting where we start, and then we're developing, because not everybody, even today, I would say, I don't know, many people would not buy this. Okay, there are a lot of arguments of everything I'm going to tell you now is solidly founded in experiments, but then the interpretation is not so clear. And we will. This is an ongoing debate. So I'm trying to get to be solid here. Okay, stick to what we know, and we'll interpret it later. But from what we knew, when we assumed that the dendrites are passive, this is a picture that we can draw. Okay. So now something happened, and this was this invention of patch clamp technique that at the beginning I told you was used to take a piece of membrane and measure single ion channels. It became in 1994, more or less, the two things happened. One of them was that people started to add, it was mainly in the lab of Bert Sackman, they started to add cameras into the experiment. And these cameras, what they allowed to do is use, instead of visible light, they let people use infrared light, and infrared light goes a little bit more into the tissue, so you can see, even if you go into the a piece of slice of brain, you can go in and you can see a little bit deeper, which means that now the cells are not dead. So usually when you cut on the top of the slice, most of the cells are dead because they're exposed and the dendrites are cut, so they're dead. So you have to look for a long time until you see a neuron that is alive. But if you can look a little bit in, you start to see many more cells. The other thing that happened is that they realized that if they apply a little bit more pressure to this piece of membrane inside, it breaks, and then you can actually record intracellularly very well. So you can get because this hole now is big, you have a very low resistance between your pipette and your cell, so you can record very accurately the membrane potential in the cell. And lastly, there was another trick that I'm not going to go into, but it's an optical trick that is kind of enhancing lines that are going in this direction and less in that direction. Okay? So with all kinds of technical small advances, suddenly they saw the neurons very well, but I don't know if you can see, but this is basically what you can see is what they could see at that time. You could see a little bit of these things going here, and these are the dendrites of these layer 5 pyramidal neurons that you can actually track all the way up outside the screen. It takes a little bit of practice, but if you look at this neuron, for example, you can certainly see that this point is still that neuron, okay? And you can even kind of look a little bit more, and if I let you play with the microscope up and down, you can go even further. Just remember that this is about 20 microns. So from here to the top of the screen, it's something like, I would say, 300 microns, something like that. And the dendrites are 700, 800 microns. So you have to watch them. If you want to go all the way, you have to watch them for another screen. So it's very tricky, but people manage to track the dendrites, and then they say, okay, if we can track them, maybe we can even patch them. And they started going and patch these dendrites. This is very difficult. Technique. And the first paper came out in 1994. by Greg Stewart. You see Greg Stewart and Bert Sackman. And we are now going to go into details on the like very, very detailed on this paper. Basically over all the figures. There are 4 figures. It's a classical paper. Okay, so what you see in the first panel is a recording from the dendrite, and you see in voltage clamp. So voltage clamp means that you record the current, and you see a very, very big current going in at this time point. Okay, here you see a very, very big current. If you put TTX blocking sodium channels, it goes away, and if you wash the TTX away, it comes back. Okay, so this what the interpretation of that is that we can record something just by looking at the size of the thing. This cannot be an ion channel, like a single ion channel. We are doing recording inside the cell, and it cannot be a synapse because of the fast time course and the size, and a synapse would not be blocked. So the interpretation is that there's something active happening in the dendrite. Active meaning voltage dependent activation of the dendrite.
How do you know it's in the dendrite? There was some echo, something happening also.
What do you mean? How do I know that it's not the spike that I record from the soma? At this time point, I still don't know that. Okay. I think I don't know why I can't see it, but I think there is a voltage, somehow a voltage step here that causes this. So we're kind of depolarizing the question.
Why wouldn't the synapse be blocked?
No, the synapse would be blocked, but I think, okay, I need to think about why we kind of assume that it's not a synapse. I think it's done in the presence of synaptic blocker. I need to check that, okay? But if I'm not mistaken, that's what it is. You can see also that it's pretty quiet, so you don't have any spontaneous activity. Okay. So now what they do is they switch to current clamp. So now they measure the voltage, and they inject the current to depolarize the axon, to depolarize the membrane. And what you see here is that they measure at different distances. So this recording was done at 600 microns away from the soma. So it's like 2 screens of what we seen before. Okay. And right now we have 1 pipette in the dendrite. We don't know what happens in the soma. Okay. And you see that the membrane potential depolarizes, and we get a spike. Okay. So now here, sorry, I went the wrong direction. This just shows you that you can get this the current. You get the current all the way up to 600 microns from the soma. So you get this phenomena not only when you're close to the soma, but also when you're going further away. And here you see the amplitude of this action potential. We call it action potential for the moment. Okay, I'll show you later why. You will see that this amplitude of that decays with distance. Okay, so this is not such a good sign. Why? Like if you would do the same experiment on axon, what should happen? Like a Hodgkin-Huxley spike. It should be the same everywhere, right? Because the peak of the spike is determined by the reversal potential of the sodium channels and not by anything else. So the fact that it becomes smaller doesn't kind of, it's kind of strange.
What's the difference between B and D? I mean, why wouldn't you expect B?
Between B and D?
Yeah.
B is a measurement of current.
So wouldn't you expect them to be related? Like here you don't see this trend.
It's true, right? Yeah. So it's another mystery. Okay. but it's not exactly the same thing. But I agree. I mean, you would expect it to become a little bit smaller, and this is kind of a mystery. Okay? We'll talk about it later. The other thing that is strange is that you see that in the soma you don't get like much difference than in the dendrite. Okay, so if you would think what you asked before, how do I know that it doesn't come from the dendrite, from the soma? You would expect here a lot of sodium current. Okay, so now they switch to a mode where they do patch recording from the soma and the dendrite at the same time. Okay, so first of all, just to convince you that this is possible, what they do is they patch with a blue color in the pipette in the soma, with a green color in the other pipette in the dendrite, and you see that the color kind of mixed in between, so you see it's the same neuron. So it's not like they patched one dendrite and then another one. Okay, and now they compare two conditions. Okay, first they inject the current in the soma. Okay, and you see that what happens is that the soma depolarizes. This is the membrane potential of the soma. It depolarizes. You get a spike, okay, which decays. I told you already that the spikes in pyramidal neurons do not look exactly like the Hodgkin-Huxley spikes. They don't kind of repolarize very heavily. So this is what the spike looks like. And then what happens in the dendrite is that there is a slower depolarization, okay, a lower one also. This is now up to this point, this is completely consistent with roll, right? So we have decay, we inject the current in the soma, we get less current in the dendrite and slower. Okay, so we get slower rise of the voltage in the dendrite. And then after the spike happened in the soma, there is something that happens in the dendrite that looks like the propagation of the spike to the dendrite. But at this point, we can't actually say if this is a passive decay of the spike, okay? Because if we will make like a very strong voltage in the soma, it will also decay into the dendrite. So maybe this is just a passive reflection of the spike in the soma, or is it something active? Okay, so we'll see that very soon. But now they replace the role, so they depolarize the dendrite. So you see now here, now the current in the dendrite starts first, and it's larger than the current in the soma. Okay, what is the other thing that you see before the spike? Before you look at the spike, just between these two, you see that the attenuation is asymmetric. You see that now we generate more voltage in the dendrite, but less is generated in the soma, so it's asymmetric. Again, like was predicted by the models. Okay, but now what happens is that the spike starts first in the soma again, and then we see it in the dendrite. Okay, this thing here is, what is it? Is that real or not? This thing here, is it real or not? You can see it here as well. What is it? Is it real or not? So this is when the current is injected. We start it here, and we stop it here. And this is the capacitance transient of the pipette. So this is an artifact. Okay, and it's bigger in the dendrite than in the soma, because the recording conditions in the soma are easier to fix. The pipette is bigger. This is technical. But you can see here when the current was injected and when it was stopped. So you see that the dendrite, so the main point here is that even when we inject the current in the dendrite, the spike happens in the soma first. Okay, so there is no dendrite there's no spike generated in the dendrite, It's only a spike that if it is active, it comes from the soma, and we still don't know here if it's active or not. But no matter what, where we inject the current, it always starts in the dendrite. Okay, so now just to make sure that this is not like an artifact of the fact that we patch the dendrite and inject current in the dendrite, they do the following experiment. They still patch soma dendrite, but then they put another pipette up here in the very far location of the dendrite. Okay? And they make an extracellular stimulation. What does that do? We just make a big voltage step in the slides.
Gives an extra stimulation. Injected.
Right, but what would it do?
Excite the B-synaptic.
Yes, it will excite the axon that's supposed to move over there, and these axons will generate action potential. This action potential will travel on the axon, and hopefully will cause synaptic release on some of the synapses that are making synapses with the soma. Now this picture is kind of idealized because we don't really know that these axons are going this way, they can go this way, they can go anywhere. We don't really know what we're activating. But we want to know that we like to think that we are injecting mostly synapses very close to this electrode. And you see that this is the artifact of the stimulation, and indeed the dendrites are depolarizing before the soma. Okay, so the interpretation is that most of the synapses that were activated here, and you see exactly what I told you before. So the synapses are activated very quickly and produce a lot of voltage, but it arrives to the soma slowly, okay, and attenuated. But still the soma start first, and then the dendrites are doing this action potential. Okay. So now what they do is they measure the delay between the somatic action potential and the dendritic action potential as a function of the distance from the soma. So you see here, these are the distances up to 600 microns, and this is the latency to the spike. So it can take almost 4 milliseconds after the somatic action potential for the dendritic action potential to start. Okay, and this looks more or less linear. And what can you draw from this curve? What conclusion can you make out of this curve? Look, you need a lot of you see how many points there are on this curve? Each point here is an experiment that they managed to patch the dendrite and the soma, okay, and measure this distance. There are probably like, I don't know, 50, 60 experiments like that. Probably on each one of them there are a few more that they haven't done. At least you want to draw some conclusion if you do all this work.
It seems to be reasonable that it will be increasing, but the linearity is weird.
Okay.
Because maybe I would expect it to decay exponentially.
Okay. Now, maybe it's idealized and it's not really linear. It's kind of, you know, when you have this point, the first thing that you draw is linear. It doesn't have to be linear. I still remember in high school that we were doing these kind of experiments with things that were, you know, Galileo type of kinetics experiments, and we had to do it on a millimeter paper and draw the lines. And we all got zeros because we fit a linear line, and the teacher told us that we should have known that it's quadratic. It's true, I mean, but which I think he was wrong, because the experiment looked like linear. And then if it happened to be quadratic for Galileo, this is a different story. But but what can you draw from this? This is a very easy conclusion that you can draw from this graph.
The farther you are from the soma, the later the spike.
Yeah, a little bit more quantitative. Come on. It's easy. This is distance, this is time. Speed, yes, the speed. How fast does the action potential go back along the dendrite? Okay, what's the speed? Okay, so this is 200, say this is 200 microns, and this, you know, I don't know, 2 milliseconds. Okay, so how fast does it go? In meters per second. No, really, I'm not kidding. In meters per second, how fast? Someone do the calculation. I can do it when I'm standing in front of you.
0.15.
Meters per second. That sounds more or less right. Okay. So, is that fast? Slow? What should we compare it to? Spikes. What do you mean? Time constant. That's relevant, but I'm looking for something else. What? Where else does spikes propagate? Axons. What's the speed of action potential in axons?
1 per 1 millisecond.
So if I have a spike here in motor cortex here, how fast does it get to my spinal cord? It has about a meter to go. So how fast does it go?
Tens of milliseconds. No.
Okay. I should know these in numbers, at least on kind of order of magnitude. So motor axons, myelinated motor axons are going around 120 meters per second. So it will take a tenth, okay? About 10 milliseconds to get this meter that they have to travel to the spinal cord. Otherwise, you know, you would not be able to do anything. It has to be fast.
But we said that the spike is about 1 millisecond, right? So it means that only 10 spikes more or less go.
But on that time,
Yeah.
I mean, these two things are not related. How are they related? Once the spike started,
Until it gets to the...
yeah, I mean, it's not the same spike that arrives, right? It can take a long time for the spike to finish here, and the spike there already kind of started. It doesn't have to wait for it to finish, right? So basically, when the spike starts, okay, it depolarizes the axon. We have myelin, so the first spikes, the spike there can start before this spike even reaches its peak, right? So the fastest spikes are myelinated axons. They can travel at up to 120 meters per second. The slowest ones are the unmyelinated C fibers, the one that carries out pain and temperature. We'll talk about it when we talk about the somatosensory system. And they go 2 meters per second. The slowest one would go about half a meter per second. So this is like on the same order of magnitude like unmyelinated axons, but even a little bit slower. Okay? So basically, if you think about it, what happens is that the spike generated in the soma, it probably reaches its targets before it reaches the dendrite. Okay, it goes much faster this direction than that direction. Okay. So remember that we said this is all nice, but how do we know it's not passive propagation of action potential into the dendrite? So here's a kind of Z proof. So what they do here is the following. They put, they again patch the dendrite and the soma, and you see in the dendritic pipette there's something called QX314. Okay, QX314, which blocks sodium channels from the inside of the pipe, of the inside of the cell. So sodium channel you can block with TTX from the outside, but with this thing QX314 from the inside. when Alex Binstock will tell you about pain, you will hear an interesting application of that idea. But here, the idea is that you put it in the pipette, and you remember that when we showed you the two colors, the color diffuses in the dendrite, but it takes some time for the color to diffuse. So you didn't see huge green color in the soma, because there's a gradient of diffusion, and it takes time, and it's also not that strong. So what happens is that when you patch the dendrite, at the beginning you only block the local sodium channels, and with time you would block more and more sodium channels along the dendrite. So you record the soma, you record the action potential in the soma and in the dendrite, and then after 100 seconds, so you let the drug diffuse, you see that the somatic one is almost unaffected, but the dendritic one is greatly reduced. Okay, and you can see it also here. With time, the amplitude of the dendritic one is going down. So this is
Where did you inject the current?
in the soma. Okay. So this is one example. I think. Okay, yes. Okay. So this basically shows you that this thing in the dendrite is dependent on sodium channels. It's not just a passive decay of the voltage. Okay, and now the last thing here, and this is an interesting observation in the paper that is not explored at all. What happens if you inject a lot of current in the dendrite? Not just enough to generate an action potential, really kind of push it to the limit. And you see that what happens here is the following thing. The dendrite is depolarizing before the soma. Soma fire action potential first. This is a dendritic action potential. But now, instead of the action potential decay, something happens, and there's another depolarization, and now you see that there's something very big happening in the dendrite, a very wide thing, okay? And this depolarization is generating another action potential in the soma, which actually kind of is ending before this thing ends in the dendrite, but it suddenly ends, even though we're still injecting current. You see, the current is between here and here. We're still injecting current, but now this thing closes down. It doesn't depolarize anymore, and then it decays passively once the current is stopped. So what is that? This looks very different, right? It's not a sodium action potential. Our best kind of guess, it has to do with calcium. It's true. But this is not explored more in the paper. So the conclusion from the paper is, first of all, we have sodium channels on the dendrites of pyramidal cells. Second, the spikes are propagating using these sodium channels, like in axons, through the dendrite, but they are propagating slowly. They are not propagating very strongly, so they don't reach the threshold. They don't reach very high amplitude, like in the soma. They decay, and also we might have calcium events happening in the dendrites when the dendrites are hit very, very strongly. Yes.
And did they know in advance that there were sodium channels in the dendrite?
No. This was kind of a surprise, and no, and it's very difficult, unfortunately, even today, to use immunohistochemistry, for example, to stain for sodium channels. The way people are using it is by staining things that hold the channels from the inside, all kinds of molecules that we know that hold the channels. But apparently, these things that hold the channels in place in axons, they do not exist in dendrites. So when you stain for them, it is called ankyrin molecules. When you stain them, you would see them in the action initial segment in the nodes of 1VA, but not in the dendrite. So in the dendrite, it seems that they are kind of floating in the membrane, but we still don't know a lot about them. So even though this, okay, so I'll just excuse myself for a second, but I will tell you that even though this paper was published in 1994, I don't know where most of you were born, but it's probably not that far away from that day, okay? We're still having a lot of trouble understanding what's going on in dendrites because it's extremely difficult to go with these pipettes and pet them, and also these pipettes are pretty big and are not very accurate, and these dendrites are very thin and hard to access. So we're using all kinds of tricks, but it's still very hard. There's a lot of things that we don't know about what's going on there. Okay.
So are they just evenly distributed in the dendrites, or do they?
So this was one of the questions. We don't know that. We don't know that so much about sodium channels, but we do know that about other channels. I'll show you some of it later. Okay, let's take a break and continue afterwards.
לגבי העבודה השנייה, הפיזיולוגיה, אפשר לקרוא כל נושא שצריך לתת?
לא, אני רוצה לכוון אתכם, אבל אני עוד לא יכולתי בדיוק מזה. Okay, so I try to convince you that the dendrites have sodium channels and that they can carry back action potential. So they're not, yes,
How general is this phenomena across the types?
we'll talk about it in a second. So I try to convince you that they have, or they try to convince us that they have sodium channels. The action potential is, if you remember, the title of the paper was active propagation of somatic action potential into neocortical groundal cell dendrites. So the action potential is back propagating into the dendrite, is not generated in the dendrite. And you remember that we talked about these, okay, in a second before that. So some of you might not have been convinced by this idea of putting this QX314, and I would kind of might agree with you that this is not like a very clean experiment because you put a blocker, it diffuses, you don't know where it goes. So here is another experiment that they did just to increase our confidence in that, and this experiment is the following. What they do is they patch the soma and dendrite like before. They put a current clamp pulse, so this is in current clamp. They put a pulse in the soma, they record the soma and the dendrite and the dendritic action potential, and now they switch to voltage clamp, okay, and they put TTX in the extracellular solution. So now there is no sodium channels open. Okay? But in voltage clamp, what do we do in voltage clamp? We clamp the voltage to whatever voltage we want, right? So usually we just, we hold the cell at -80, we jump to -40. But you can actually clamp the soma to the same shape of the action potential. You can actually replay this voltage into the voltage clamp, and when you do that, you see exactly the same voltage in the soma because you actually force the voltage at each time point to be what you want. Okay. At the same time, you can record what happens in the dendrite. Okay. So the soma is in voltage clamp, but the dendrite is in current clamp. So the dendrite is recording voltage, and you see that the voltage in the dendrite does not look like the spike that you see when you measure in current clamp. So this is what the passive attenuation into the dendrite would look like, and this is what happens when you have sodium channels. Okay? So the conclusion is, indeed, that the sodium channels are carrying out this backpropagating spike. So this is just to remind you, remember the Softy model that assumed that there are sodium channels in the dendrite, and if two spikes are coming together to a dendrite, they will generate an action potential because the voltage in the dendrite transients are so big, so two would be enough to cross the threshold. It doesn't seem to work here. Okay? It doesn't seem that the density of sodium channels in the dendrite are enough such that small synaptic input will generate action potential in the dendrite that will propagate into the soma. At least not in this case. Okay? I don't know if I'll have a chance to show you other cases where things like that might happen. Okay. This paper was followed by basically, I don't know, a tsunami of work on dendrite. So there were few labs in the world. Basically, all the postdocs that were at that time in Tuckman's lab, and another lab in the United States of a person called Daniel Johnston that were doing more or less the same things at the same time. They were doing this experiment of patching dendrites. Each one of these postdocs published a paper in Nature or Science, and then opened his own lab and started patching dendrites, and there was basically a tsunami of experiments and papers. These are just few titles from these things, so there's no way I can cover all of them. It's a whole course or even more. just to understand what's going on in these dendrites. Most of these works were done using the same technique of this attachment, and I will just try to show you some highlights of the things that were discovered by these people. So the first question was really like you asked, is that happening everywhere in all neurons? And this is kind of a summary of few cell types that were tested. So one of them was in dopaminergic cells in the substantia nigra. The spike seems to work almost like in an axon. It doesn't decay with distance. In all the cells that were tested, the spike was backpropagating. Okay? So it was. I don't think there is a case which we know of where you depolarize the dendrite and you get the spike first in the dendrite and then in the soma. So it is kind of agreed that the spike is generated, this is another question, in the soma or the initial segment of the axon. People tend to think that it starts at the initial segment, not in the soma. The soma is more or less like the dendrite. So actually the spike generated in the axon backpropagating to the soma and then backpropagating to the dendrite. Basically, not like with a stop or something. It's just kind of backpropagating from the axon into the soma and dendrite. Okay. Neocortical pyramidal cells. These are the ones that I showed you, and this is also true for layer 2-3 pyramidal cells, not only for layer 5. Another cell type that was very much explored is a CA1 pyramidal neuron of the hippocampus, and this one also has a decay of the action potential. And in motor neurons, there is also a decay of the action potential into the dendrite. And the one that stands out is the one that we started with, which is a Purkinje cell. And the Purkinje cell the spike does not propagate almost at all into the dendrite. As you remember, I don't know if I can show you that, this work of Linus and Sugimori, you already saw that these action potential simple spikes, they do not really propagate much into the dendrite. And it turns out that with histochemistry, that Purkinje cells do not have sodium channels in the dendrite. So there is no mechanism to carry back the action potential into the dendrite. Okay, this is one thing that people have shown, that basically this is a general phenomenon. All cell types that we know, the spikes are backpropagating into the dendrite except from Purkinje cells. Okay. Another paper that made a lot of influence is this paper by Hoffman from the lab of Daniel Johnston. And what they did is they went and did, instead of intracellular recording from the dendrite, cell-attached recording, so kind of single cell, if you want, a single channel recording along the dendrite. And they measured specific type of currents. For example, in this case, this is a potassium current, which is called IA. I've shown you last class about this current. And what you see is that the density of the current, so basically the amplitude of the current, you can see it here. You hyperpolarize a cell, you open the current, and you get, what you get is a lot of current, some current in the soma, a lot of current in the dendrite. So basically the density of the current increases as you go along the dendrite. So this picture that we saw with the sodium channels, that seems to be uniform along the dendrite, no matter where you measure the density of the sodium channels, this is not true for all ion channels. For example, potassium channels, you have more in the dendrite than in the soma. Okay? And this might explain why the action potential amplitude actually decays with distance. Because while the sodium channels are the same, the potassium channel seems to increase. Okay, so there's something that closes the spike when it goes into the dendrite faster or before it reaches the peak, and this is why we get attenuation of the action potential as it goes into the dendrite. Okay? That was another one. Okay, so is it good for anything? So I can't, this slide, maybe I should keep for the end of the course where we talk about plasticity, but one of the, okay, let's do it as a discussion first. What would it, why would it actually be, why would anyone get the idea that backpropagating action potential is good for plasticity? Yes, what about it?
You need depolarization in order to open the NMDA channel.
Right. Anyone kind of following? Is it clear for everybody? So you know that for LTP we need to change synaptic potentiation, we need to release the magnesium block from NMDA channels. Okay? And then the question was always, which in some ways was my first question when I met Udan as a PhD student. I told him, like, we're talking about heavy ion plasticity, but how does the synapse that sits there on the dendrite knows if the soma spikes or not? Okay, and now we have a mechanism basically to implement heavy ion plasticity, because we know the synapse now knows when the soma spikes, because we have the backpropagating action potential. It goes into the dendrite, and it mechanistically can do that by releasing the magnesium block from the NMDA receptor, and then we can induce plasticity. So we'll talk about this more in detail when we talk about LTP, but one of the things that people have shown, maybe without going into the details now, is that you can manipulate LTP by manipulating this backpropagating action potential. Maybe we'll skip that one. I put here, this is a slide that talks a lot about numbers in dendrites. I'll put it in the slide so you have reference if you ever need to know some of these numbers. And I'm skipping that because it's less interesting. I'll skip that as well. Okay, so you remember that one of the things that we have at the end of this of that paper by Greg Stewart was this thing that shows that there might be something interesting happening in terms of calcium. Okay? So the story goes the following: there were many people, I mean, about 6, I think, postdocs together when Greg Stewart was doing that in the Sackman's lab, and they all were very excited about this technique of dendritic patching. So what they did is, like, one took the CA1 pyramidal cells, and one took the dopaminergic cells, and one took the cerebellum, and kind of split the wall. And the last one, it's like Savta Bishla Daisa. The last one that was left was Jackie Schiller, which was left with no general big neuron to patch the dendrites for. So what they did there, they divided the neuron. So they took these layer 5 pyramidal cells, and since it was very difficult to patch beyond 600 microns, she took the apical tuft, and she used imaging rather than patching. Okay, so she was doing calcium imaging in the apical tuft. When you do injection of voltage, basically this was the first thing that they were doing. So when you do calcium imaging, basically what you do, you fill the cell with a dye that is sensitive to changes in calcium concentration. Okay, and what you can see is that sometimes you get these calcium events in the dendrite with no almost no change in when you get to proximal things in the soma. Sometimes even without even seeing a lot of change in the voltage in the soma. Okay, so something is going on with calcium in this apical tuft, and she had to basically sneak into the lab and try to patch at night when no one knows, and go and patch more distal than 600 microns in order to see what's going on there. And it turned out that now you can give like stimulation into the dendrite and that generate these dendritic spikes in the dendrite. Okay? Where you see that at the same time you have some depolarization in the soma, but it's not like an action potential. So what you see here now is not a backpropagating action potential, but it's an action potential of the dendrite. But it's not a sodium action potential, it's maybe a mixture of sodium and calcium. Okay? And then she left, and someone else, Matthew Larkin, came to the lab, and he did this, I think, second classic experiment that I'm going to go a little bit in detail on. So he already kind of managed to patch the dendrites at very long distances, more or less regularly. So he was doing the following thing. He was patching the dendrite and the soma. So you see this is a red electrode dendrite, black electrode soma. And now he was injecting a current that looks like a synapse, like a synaptic input into the dendrite. So you see current stimulation. You see that it looks like a synaptic current. And you see the voltage in the dendrite that looks like a synaptic input. But at the soma, what do you see at the soma? Nothing, no effect. Surprising or not surprising? Not really surprising, because we know there is a huge attenuation. The current is not very strong. The voltage is not very big. So basically at the soma you don't see anything. Okay. Now you switch roles and you do the opposite. Now you inject the current in the soma, and what you see is the action potential in the soma, and not surprisingly, few milliseconds afterwards you see the backpropagating action potential in the dendrite. So far so good, we know all of that, but now you combine the two. Okay, so you inject the synaptic input in the dendrite and the current that generates an action potential in the soma. And what you see is something that is not so much expected. Okay, so this action potential that is backpropagating into the dendrite is generating this backpropagating action potential. So sorry, the somatic action potential generating this backpropagating action potential. But then this small depolarization in the dendrite that has no effect on the soma, somehow instead of letting the dendrite depolarize, hyperpolarize, it's depolarizing it. And then you get this kind of very long dendritic voltage thing. Okay, I don't know how to call it. It's spike or whatever, calcium spike. And it's so big that it depolarizes the soma enough to generate two more action potentials. So at this time point, there's no current injected in the soma. All that happens because of the dendritic depolarization. Okay. And this dendritic depolarization is very far away from the soma. Generally, usually it doesn't do much. Okay, but now when you kind of when it goes, it opens this calcium spike in the dendrite, it generates this action potential into soma. Just to make sure, if you inject a lot of current in the dendrite, if you inject a much bigger stimulation in the dendrite, you can generate this calcium spike alone without the soma, without the backpropagating action potential, and indeed it will generate these kind of two spikes on its own. So this was surprising in two ways. One of them, it's highly nonlinear, right? I mean, from a linear system, you would expect that if you combine this experiment with that experiment, what you should get is basically that, right? Because in the soma, that thing doesn't do anything. So it's highly nonlinear. And the second thing is that it's important in the sense that when you read a little bit about these cells, you realize that they span the whole cortex. And this region of the cortex, this apical tuft of the dendrite, gets inputs very different from this area of the somatic region. Okay, so the axons that arrive here are mostly axons of layer 5 pyramidal, other layer 5 pyramidal cells, or layer 2-3 cells that project downward, also, or thalamic inputs that coming inward, depending on which cortex you look at. But in the apical tuft, there is like a very, the layer 1, the apical tuft is in layer 1 of the cortex where there is a lot of inputs that traveling from far away. So many axons coming from all over the brain, also from the thalamus. So what they thought of, this is actually a kind of a mechanism to bind these two type of inputs. So if this input arrives on its own, doesn't do much. If this input arrives on its own, it's making regular spikes. But when they coincide, they happen together, then you get a different type of output. And this different type of output can actually signal that something special had happened, this burst. Just to show you that it really depends on the timing. So what they do here is they do the same experiment, but now they shift at the timing of when they inject the synaptic current in the dendrite. Okay. So you see here, now the input comes, and a little bit afterwards, the synaptic input comes, or the dendritic input comes. Here the delay is longer, and here the delay is even longer. Okay, and when you do that, you see that this, if the synaptic input comes too early, you don't really get another extra spike. If the delay is certain, something like 5 milliseconds between this current and that current, you get this burst. But if it's longer, even longer than that, again, you don't really get the extra spike in the output. Okay, so it depends on the timing. And you can also measure it by how much current do you need to inject here in order to reach that threshold. So maybe here, if you increase the dendritic current, you can actually push that thing up and generate another one. But you will need a stronger current. So if the current doesn't come in the right time, it needs to be larger. Okay, so it's a complicated thing, and it has here, you see the calcium amplitude as a function of the difference in timing. And you see that there is a perfect time in order to generate it. So this is interesting. It's also interesting in the term, in a second. It's also interesting in the context of what we talked about timing before. You remember that we talked about, Nun has mechanisms to be sensitive to timing. This is a kind of an example where timing is extremely important. Okay, if you think that this thing is important, this burst versus non-burst, like 3 spikes versus 1 spike, are important. If you would look at this in terms of rate, right, this is like you go from regular firing rate of 10 spikes per second suddenly to 100 hertz. Okay. So if you think even in terms of frequencies, this is a mechanism that is highly sensitive to timing. Yes.
I don't know if it has any point, but it's a little unhappy, and no, like you have to get the inputs after the spike. The optimal condition is to get the inputs after the cell already made the decision.
To spike.
Yeah.
Right.
So
In
like
some ways,
non-causal in some way.
well, it's true and not true. I mean, it's non-causal in the sense that it happened after the cell made the decision. I agree with you. But on the other hand, it's kind of, if you think about the input that drives the spike into the soma, and the input that arrives to the dendrite, if you look at these two inputs, then in that sense, it's kind of insensitive to what the soma decided to do. But I agree with you, it's true. I mean, it comes after, and it's, in that sense, it's non-causal. I agree. It's also even more confusing in the sense that you think, okay, if we have such a big calcium event here in the dendrites, probably it has some effect on plasticity of the synapses, right? So synapses that were activated after the cell decided to spike would be potentiated, and it's true. In that sense, they are non-causal, right? Okay, just to show you that this happens not only with dendritic, as you can see, there is, so I want to highlight these two papers came from Sackman's lab in a difference of 5 years. You see that they are very, very similar in terms of like cleanness, you know, how clean the data is presented and how everything is perfect. And also following in many ways the same logic. So remember that experiment where we kind of stimulated the extracellular axons to show that it's not the dendritic current injection that is important, but it can work in the real world. So here they repeated it in the same way. They did this extracellular electrode generating spikes to generate real synaptic input, and somatic electrode in order to generate current in the cells. And you see here again the same phenomena with real inputs. But they even went one step further, and this is really kind of a heroic experiment. So what he does here is patch the soma, the dendrite, and also patch an inhibitory neuron that is very close to the pyramidal cell. And what you see here is that you get the phenomena. Okay, you inject current in the soma, you inject current in the dendrite, you get this huge burst of calcium spike and a burst of action potential. And now, at the same time that you stimulate the action potential in the soma, you also stimulate an action potential in the inhibitory neuron. Okay? And what you see is that this inhibitory neuron is generating a huge inhibition in the dendrite. And then this current that you inject in the dendrite is not enough now in order to generate the calcium spike, and you don't get the burst. Okay, so a single inhibitory neuron can veto this phenomenon. Okay. So I want to highlight here, I forgot to show you. I didn't show you the title. Okay. So, sorry, something is strange. Although these papers came 5 years from one another, the first paper was just talking about the mechanism, the fact that backpropagating action potential are backpropagating into the dendrite. This paper already talked about coincidence detection, so it switched basically the focus from biophysics, which is still the core of this paper, but to the interpretation of what this thing can do. And this is coincidence detection, like computational function of dendrite. Okay? And this was kind of another line that was going in parallel all the time when new facts about dendritic integration came and became more apparent. People always try to associate them with some computational questions. I don't know why this is here. I thought I moved the slide somewhere else. Okay, so let's talk a tiny bit about computations. If we are already, let's talk about that. Okay, so already in around the same time that Greg Stewart did his first dendritic recording, about 92, someone called Bartlett Mell was doing modeling of neurons, and he was interested in NMDA receptors, and the fact that NMDA receptors are sensitive to the voltage. And you remember that we talked about the fact that synaptic in the dendrites are generating more locally, more depolarization than the same synapse located onto the soma. And you remember this, just to put it in context, you remember this image that we started today, was we said that when you put two synapses together, you actually lose because they are shunting each other. They're kind of depolarizing and reducing the driving force. But he was thinking, okay, maybe they do that, but maybe also they depolarize the membrane, and if there are NMDA receptors, this will recruit NMDA receptors, and this can actually overcome what you lose here. So he was doing the simulation, the following simulation that I'm showing you here. And what you see is that what he compares now is that a case where he take a CA1 pyramidal cell in the hippocampus and distribute the synapses randomly on the dendritic tree. And let's ignore the middle one and take the same neuron with the same number of synapses, but now we cluster them. So we put them on the same dendrite in groups. So some of the synapses are coming to the same dendritic branch as a group, and another group is going to another dendritic branch. We still activate them randomly, okay? But we kind of tend and kind of put them together on the same dendrite. And you see that in terms of effectiveness of generating output with the same number of synapses, this case is much more effective than that case. Okay? So if we distribute them, and remember from passive stable theory, we should have lost. If we distribute them, we should win, basically. We should generate more current, more voltage. But still we get less action potential. And if we do it here, clustered, we get more action potential. Okay, so he basically started this idea that maybe by clustering inputs, because of NMDA recruitment, we can actually generate locally a lot more voltage and actually boost the input, get more than we were supposed to get just by passive properties.
Sorry, I'm a little bit lost.
Yes.
What's the difference between the yellow door and the green door?
So I think what he did here, if I remember correctly, he said, okay, let's take some of the inputs and cluster them, and the rest will just, what would, okay, let's say out of 100 synapses, 50 will be clustered. So like 10 here, 10 here, 10 here, 10 here. Okay? And then the rest will just distribute randomly. So then we get an intermediate case where some of the input are clustered and some are distributed randomly. Yes.
This is a bit of an undefined question, but does this have an implication on the salt and pepper organization? Because the salt and pepper in the one clustered, would it be more efficient, or I don't know?
Yes.
Hold your breath.
Hold your horses. We'll talk about it. In fact, one of the the papers that you have to review is dealing exactly with that question. It's one example of a paper that is dealing with this question. Okay, so independently, whether she was aware of this paper or not, I'm not sure. Jackie Schiller, when she went for a second postdoc, she was actually looking for local effects of NMDA, and she discovered what is called NMDA spike. I'm skipping now talking about the details of NMDA, but what she did is the following. She was patching a neuron, filling it with a dye, and then taking another, so because it's filled with a dye, you can even see the very thin dendrites that before, when I showed you with the infrared camera, you can see the apical dendrites, but all the small dendrites, the small ones that are going in all directions, very, very difficult to follow, you can't see them. But if you fill them with the dye, then you can see them. You still cannot touch them, but you can put another pipette very, very close by to this dendrite, and make an extracellular voltage, hoping that axons that are just, going in this vicinity and synapses on the dendrite would be activated. Okay, so this is what she did. And you see here what she's giving one pulse, and right after that another pulse, so it's two pulses, so one depolarization and then another one. And you see that if you give one pulse and then another one, which are small, you get an EPSP. You increase the pulse, the size, you get a bigger EPSP. You increase it even more, a bigger one, and then suddenly you get something which is huge, and nothing in between. Okay, so you switch from something that is increasing linearly with the amplitude of your pulse to something that is much bigger. Okay, so this is the increase with the pulse intensity, and suddenly it jumps and almost doesn't change the shape. Okay. If you put AP5 is it's an NMDA blocker, it's blocking NMDA. Then it is gone. So it's kind of going, first of all, the individual EPSPs become smaller, because apparently there is some NMDA in each one of the responses already. Okay? So it's becoming smaller, but also it increases without this jump, so it becomes kind of linear. Okay, so this was 2004, and this phenomena was called NMDA spike. That's just another example of something. And you can kind of do all kinds of other experiments of comparing inputs that are on different branches versus the same branch. Within branch versus between branches, and you see that if it's between branches, it goes linearly, but if it's within branch, it goes at the beginning linearly and then jumps in such way. Okay. So the individual branches seems to be nonlinear. So if you increase your input more and more and more, suddenly it jumps. Okay, so we'll talk a little bit about the interpretation in the next class. I just want to show you that 2009, Schiller and Larkum, they did experiment together with a guy called Thomas Nevian and Alon Brodsky. And what they did here is now switch from layer 2-3 to layer 5 pyramidal cells, use 2-photon microscopy so they can actually see the dendrites and actually patch them. Okay, and now they repeated all this combination of experiments of NMDA spikes and also this back thing, so this calcium spike that you have in the dendrite. And what I want to show you is two things. First of all, this NMDA spike happens not only in the basal dendrites of layer 2-3 pyramidal cells like Jackie Schiller showed, but they also happen in the apical tuft of layer 5 pyramidal cells. So what you can see here is like a blue electrode on the tuft and an extracellular electrode that is stimulating the axon, and you can see that you can get these NMDA spikes. And the other thing is that you can, by combining two NMDA spikes on two different dendrites, you can generate an action potential, a calcium action potential in this area of the dendrite, and then the figure that kind of concluding this paper is this view of, like the modern view of a pyramidal neuron, if you want, which has a soma that can generate, or axon, that can generate sodium spikes that goes in the axon, but can also go back in the dendrite, like Stewart and Sackman showed. Okay? You have the calcium spike in the dendrite that can propagate to the soma and make more spikes like a burst. And then you have NMDA spikes on all of these branches, both in the apical tuft and in the proximal area, that can interact with each other. So two of these can generate that one, that will generate a burst. But also, if you get an input that comes here, coincidence with input that comes to the dendrite, they can also generate this backpropagating, by the backpropagating, and the local voltage can also generate a calcium spike that will end up with the burst. Okay, so this view is in contrast, sharp contrast to the things we started with at the beginning of the lecture, when we saw this passive picture of this cell as something that just summates input passively, where most of the input cannot do anything to the soma. It's not true. And when Idan told you that, you know, what we think today is that we cannot neglect anything, is some of it is because, you know, these inputs here may be on its own. Each one of them, they don't do much, but if they summate together, they can generate calcium spike, NMDA spike, and influence a lot of what's coming out of the output of the neuron. Okay, we'll end up now. And continue on next Tuesday. Okay.
I have a question about assignments. So some papers have supplementary material that you have to write.
You have to look at it if it affects, you know, because maybe you have like a criticism and they kind of answer it in the supplementary material. And you have to kind of at least address it. You can, it would be kind of, I think, reasonable to assume that when you review the paper, the supplementary material wasn't there. Because a lot of times the supplementary material is a response to the review. But I mean, don't neglect it completely because it looks strange.
I got a question about the clustering things you were talking about. In the simulation, where the synapses were clustered or the nucleus were clustered, on average the cluster was closer to the soma than when they are dispersed. So isn't it expected that if on average they are close to the soma, it will not the fact show the fact that they are clustered?
It's a good point. I don't know if they control for that. I mean, if I would want to make this point stronger, maybe I would make sure that all the clusters are on average longer, further away. I think it's a very point. I don't know if they control for that at this point. But I think it will still work.
Yes.
Another
וואי, היום בבוקר הוא ממש ואז אמרתי לי, יוליה, אני
if you give it to here and here, so you will get strong excitation here, right? Yeah, but if you give here and here, so it will be lower compared to this one, right? But if the model is quite different, so it contains the excitation and the so maybe this will be higher than this. Okay. So the difference is one is passive, one is
כן, תהיה עכשיו כמה של הספר, מה הוא אומר, כאילו,
Probably need a pair of earrings.
You don't have anyone?
Yeah, I'm looking to anyone. People I know.
Okay, I'll try to see what I can do. Okay?
Thank you.
אולי נעשה... כאילו בקטנה כזה, לא משהו עצמי. סתם כזה, נלך למקום שאפשר לישון. אולי מדהים. אני ממש שמחה שתכנתי אותך ללכת באוטובוס ותכנתי אותך.
כי אחרת הייתי הולכת בכל מקרה בתחנה. לישון.
תגידו, ביום שיש לי היום כאילו הופעה, שאח שלי כאילו קיבל את הספין במתנה, והוא החליט לקחת אותי, איזה חמוד. כאילו, אז אני מרגישה כאילו אני חייבת כזה ליהנות, ואני נורא עייפה.
אבל אתם...
אני חייבת, ואני גם חייבת כאילו לבוא במוד כזה של... באיפה ליהנות?
איזה הופעה?
של גרדן סיטי ברוקלין. לגמרי. כנראה בשטות הזאת. את לא יודעת.
איך הוא קיבל את הסרט? אני הייתי
שמעו לו כרטיסים ליום הולדת. יואו, התיק שלי שוקל איזה 200 קילו. תחזיקי? הוא כבד שאין דברים.
הוא כבד יחסית, אבל זה
באמת?
כן.
באיזה קטע?
לקחתי מלא דברים לסופש.
גם אני. ואני לקחתי גם מזוודה.
באמת?
חצי ריקה.
אז זה כזה להביא אוכל.
זה להביא מלא דברים שכאילו... קודם כל אין לי מכונה. שזה איזשהו...
זה ממש מביך.
אישו קשה בחיים שלי.
להסתובב ב50 מזוודה. רק כזה רפואנים עושים.
אני באמת נורא מתנצלת, אין לי מכונת כביסה בבית.
לא, בסדר, אני עושה את זה עם תיק כזה.
כן.
טיולים, אבל...
לא, אז אין לי תיק טיולים. אני מתארת נראה לך. מתארת מהמיטה לפה. בנוכל רוצה לחזור למיטה, מה כאילו? אבל... התוודעת נורא, את זוכרת את זה למטה באוטובוס, ועלה בבעלה. כאילו, מה אני צריכה את זה על הגב שלי?
לא אמרתי שזה לא נוח.
אתה יודע איך הגב שלי? אין לך מושג. זה בעיות של אנשים גבוהים מגיל צעיר, יש להם בעיות גב. קיצור, יש לי גם בנובר.
יואו, קראתי שיש גם חבילות גדולות של פעם.
וואו, אני כל כך רוצה. 150 גרם. זה 60. איפה זה 150 גרם? זה מלא כל זה.
כמות נאה ביותר.
וואי, כאילו, הקטע המגניב הזה חשוב לקרוא את זה כתוב הזה בקולנוע.
לפעמים כל זה כתוב
קודם כל יש בנק בחלבה בעולם, זה יותר טעים.
אני גם ממש אוהבת.
גם בחלבה כפו את פעם אחת.
היה את הפוסט הזה בפייסבוק על מישהו שכזה פילח מקרם בנוגש וזה, וממש התלהב, וריאל לקראת החוויה, והיה שוקל נוגש כזה, וקלט שזה במבה בלי נוגש.
במבה רגיל?
כן.
לא.
זה לא החיים.
כן.
במבה רגיל?
הוא לא שם לב שזה לא חום.
לא, זה היה בתפילה כזאת, זה היה כאילו תקלה של אוכל.
וואו, כמו שפעם אחת אני קניתי גומי גם ולא היה בפנים גומי אחד.
מה? חשבתי שלא סופרים בשלושה.
שתדע שפעם אחת יצא לי 5. וביום הזה רציתי לעצמי מלא גומי.
אגב, לא אכלתי גומי גם.
בסדר. וואי, תודי קטנה, משוגעת מסורת. הייתי קטנה, אני ואח שלי, ששתיים היינו ב3 שנים, אוכלים גומי גם, והוא תמיד היה מאוד מחכה אותי, וכל מה שהייתי עושה לו הלכתי גם. כיף כזה שלכם קטנים. והייתי כאילו בזה 6, 7, כאילו לא ידעתי את הסכום של הבן אדם, כן? וכל פעם הייתי הולכת את הגומי גם, סבתא הייתה מביאה לנו צלחת, כי אסור לאכול כלום בזה, כמו שזכרתי, כאילו. הייתי אוכלת את זה מהצלחת, ומוציאה את הגומים כאילו, שומעת אותם בצלחת. ואז זה גם. ואז בסוף הייתי אוכלת את הגומי, והוא היה יותר מכניס גם, כי הוא רוצה להדביק את הפער. אבל הייתי שומעת את זה כזה בפה ומראה, שסמיין אותי לגומי, והוא היה אוכל גם. ואז צלבתי את זה והיה לי יותר גומי מלא.
אומייגאד, איזה מסכן קטן. אני רוצה שלאחות הקטנה, ושנאתי את אח שלי, הוא היה גם מתעלל בי, שנאתי אותו.
אני לא מבינה איך הייתי מתעלל עצמו.
זה נורא, למה אתם עושים את זה? יאללה, מאפים.
כאילו במי תתעללי?
בן אדם מעריץ אותך.
וואי, הכי מצחיק בעולם. כאילו כשהגענו בזיכרון, אז אמרתי לו ששכנים יש כאלה מסתדר עושים במוצאת. כמובן שזה חוזר נזק, והוא לא קרא, הוא לא הכיר. טוב שזה אמיתי. כדי להעצים את החוויה ברמה כזה, זה לראות רעיון.
הייתה תקופה שהייתי עושה כזה דברים בשביל אחי, כאילו הוא עושה אותי לעשות בשביל הטובות, כי הוא אמר שהוא כזה בטוח יטוס עם הכיתה שלי ל6+, ואז כאילו אם אני לא עושה בשביל הדברים, אז הוא לא יבין אם מפגרת שהוא יטוס. אז גם אני מפגרת בסיפור הזה, חד משמעית, אבל מה עושה קצת?
המציאות שאומרים לך, זה חרא.
אבל סבא כן בטוב, אנחנו לא בטוב.
באמת?
כאילו סתם, מה זה לא טוב בטוב, אנחנו לא מדברים פשוט.
מדברת עם עצמו.
למה?
כאילו לא מדברת, אנחנו לא עוברות, פשוט אין אינטראקציה.
למה?
ככה כן, אנחנו בקושי נראים.
בין כמה הוא?
אני חושבת.
כאילו בכמה הוא גדול ממך? איך זה יכול להיות?